So in this video, we are going to talk about Monty problem. This is a very interesting problem that puts your intuition into a test. This is like a game. It's a game of guesswork. You have to guess something. So that means the game involves probability. To win the game, your intuition may tell you to do something that would be in contradiction to what the mathematics of the probability would say. So that's why it's really an interesting game, which tells us that ultimately the truth can never be achieved with certainty by the means of intuition. So you shouldn't always follow what your intuition say. Rather, you have to find out an analytical, rigorous, mathematical approach and a scientific inquiry to search for the truth. And that's the best practice. Now, what is the game or what is the problem here? So in this problem, what we have is a host and a player and 3 boxes, and there is a ball that host has. So there are 2 persons involved, one host, one player, and then there are 3 boxes A, B, C and a ball. Then one of the boxes contains the ball. So at the very beginning, what the host does is he goes and puts the ball randomly into one of the boxes. So the player doesn't know that the ball is in which box, but the host does. Then the game is that if the player wants to win, then the player has to make a guess, and a correct guess that which box contains the ball. So the game happens in this way. First, the player makes a guess and chooses one of the box. Let's say he chooses the box A. Then next, the host opens one of the remaining 2. So if the player chooses A, then the host go and opens one of the boxes. One of the which boxes? Which one is empty? The host knows which one is the empty. So he opens one of the empty boxes. Let's say that empty box was B, so he opens the box B. Next, the host asks the player who was already choosing the box A that, you see, now the box B doesn't have, it's empty, it doesn't have the ball. So he would ask the player, would he want to switch his choice? Would he want to change his mind and go for the box C? Now the question is, what should the player do? Should he stick to his first choice, or should he change his mind and choose the box C? Now, to understand what the player should do, what we have at the very beginning, the host randomly puts the ball in one of the boxes. So for the player, the probability of the ball to be in one of the box is 1/3. They're all same, 1/3, 1/3, 1/3. So the box randomly A was chosen by the player, say. Then what's the remaining 2 boxes? What's their probability to have the ball together? This box B and C, their probability is 1/3 plus 1/3 that the ball is either of these boxes B and C, right? So now with this, the host comes and opens the box B, let's say, and it's empty. When it is empty, then what happens? Its probability goes to 0. So earlier B and C combined, their probability was 2/3. Now the box B, which is already open and it's empty, its probability goes to 0. So the total probability shifts to the box C. Now, when that is the case, next, after the host chooses the box B and asks the player if he wants to switch from A to C, what should the player do? Of course, he should switch, because in that case, his probability of being correct that the box C contains the ball is 2/3. And if he sticks to his original choice, then his probability of being correct is 1/3, right? Now, so that's how he should make the choice. There is a wrong way to approach this problem. So to understand that wrong way, let's think about the problem again. So now the player has chosen one of the boxes, and all of these boxes have the same probability. Then the host comes and he chooses the box B. So now its probability is 0. Here comes the crucial part. You may think in this way that, okay, the box B do not have it. The box B is empty, but still it's not clear whether box A has the ball or C has the ball. So that means, what is the probability that now the ball is certainly with either A or certainly with C. So that means the box A would have a probability half and C would have a probability half. So in that case, there is no need to switch for the player from A to C, right? But that's not the case. Why I'm saying so? We'll show you by running a program. So what's the conclusion? the Monty Hall problem, the player needs to always switch to double his chances of winning. If the player chooses not to switch, then he has a 1 in 3 chance to win. If the player chooses to switch, then he has 2 in 3 chance to win. And yes, one last thing about the probability. In such a game, in one instance, these two probabilities may not give you the correct outcome of the game. So what you have to do is you have to play the game n numbers of times, large numbers of times. And then in some of the games, the player would, even if he switches to the C, he would lose. But some of the times he will win. So he would, after all the game, if you count how many times he won, you will find that he won 2/3 times if he switches. And if he doesn't, then he will win only 1/3 times, right? So this much is about this problem. Now let's go and check out our problem in a different way. So here I have written a program. So in this program, what I have, this is a C program. So it has its own structure. It starts with some header file and then main function and so forth. You don't have to much pay attention to those details. What you just have to know that what I have. What I have is how many times I want to play, 100 times. How many bags do I have? 3 bags. And then these two variables are like how many times I have won out of this 100, and for a particular game did I win or not. So these two variables will contain that information. So then I am having a loop here. So that loop runs for n play times. So how much is n play? N play is 100. So 100 times this loop will run. And in this loop, if it goes just one time, then it's like I'm playing one game. Then it comes back and runs again. Then it's another game. And this way it runs again and again. That's why it's called loop. So it plays n play times. Now at the very beginning, before the host starts the game, what the host would do, first he will start with empty bags. And then he would put the ball. So here, this line is like emptying the boxes. And then he would choose, okay, which one I have to put the ball. Okay, first one, second one, or the third one. So this line is for that, to choose which one. And then this line is to put the ball in that bag. Anyway, so then he asks, the game starts, he asks the player to choose one of the boxes. So this line is for that. Then the player chooses one of the box 1, 2, 3, and so forth. So that's why this number is here, 3. So he chooses one of the boxes out of 1, 2, 3. And then next, next step is for the host to open one of the boxes. Host opens which box? He doesn't open the box that the player already have chosen. So the player have chosen which box? The PID box. So he would not choose this one. And then also he would not choose, he has to choose the empty one. So he would not choose the one which contains the ball. Which one contains the ball? The HID. So this two line is making sure that. So HEID is the bag which he opens, right? So up to this, now the host has also opened the bag, one of the box. And next he asks the player whether he wants to switch. So the player, if he switches, then his probability is 2/3. That's what we have seen earlier, right? So, but if he doesn't, then we are saying that he would lose. Okay. And we'll keep a count, how many times he lost if he doesn't switch. So this line is this, that he have chosen this PID box, one of the box, and if the bag of that box means is not is equal to 1, means if that bag or box doesn't contain the ball, then we say he lose, win is equal to 0. Otherwise he wins, means he makes the switch, right? And then we just add 1 win to the n win. So this is like how many times I have win, and that count is this n win. And the loop ends here, and at the very end I take a ratio, number of times won and number of times played, right? And this line prints something. We'll see what it prints. So now let's try this program. Now to do that, let's go back to this terminal. So let's compile and then run it. When we run it, what do we get? These are the different numbers of runs. So these are like different games. So in the last game, what is going on? The ball was in the third box, but the player has chosen the box 1, right? So the host has to choose now one of the empty box. So he has chosen box 2. Now the player has to switch. So he would switch from 1 to box 3 because 2 is empty, which was opened by the host. So in that case, the moment he switches from 1 which is left, and there is 3, the player wins. Now, whereas here, what is going on? The ball was in the second box, randomly chosen at the very beginning. The player chooses the second box itself, but host chooses one of the empty box, and that is 1, the first box. But then the player needs to switch, so he switches from second box to the third box, but the ball was in the second box, so he loses. And this way, for each game, there are this win and lose, and then when number of win is divided by the number of play, that gives you what's the ratio, what's the probability with which he won, the player, and it turns out to be 0.71. And this is this ideal 2 by 3, 2/3. So what happened? Why it's not 2/3? Because here the number of games that we played is very, very small. The mathematical probability, to achieve the mathematical probability, you have to play the game for a large numbers of times. So let's change this to 100,000 and let's see what happens. And in that case, because this will take lots of time, so let's switch this print statement and see what happens. So we compiled again and we are now running it. Because I switched off the printf statement, so it will not show us these lines, but anyway it will show us this last line, the result. So what is it? Earlier when I ran 100 times, this is 0.71. now 100,000 times, it's very close to now the ideal probability, which is 0.6678. if I increase it by one more number, so it's like now 10 million. So I'm playing the game for 10 million times. In that case, what should be the result? It should be further close towards the ideal probability. Let's see what it comes. So in that case, earlier it was 667, now it's 666588. So that means if you increase it further, then we'll reach towards the mathematical probability. With this, we end our presentation for the Monty Hall problem.